We know quite a bit about the cosmic microwave background radiation, which is about 380,000 years after the Big Bang. And we know quite a bit about the time when the first galaxies were starting to come together within a few 100 million years after the Big Bang. But there is this time in between, a time when the universe was not giving out a lot of light, that hydrogen was in giant clouds that blocked all of the activity that was going on inside. This is known as the cosmic dark ages. And it's really difficult to observe a place that is dark. And yet there's this trick that there is this specific wavelength of light that neutral hydrogen will give off very rarely, and yet it happens enough that you can actually probe and scan this time in the universe. It's called the 21 centimeter line. It's a very difficult observation to make from the surface of the Earth. We have the ionosphere above us. We have all of humanity's radio emissions that will obscure and make these observations almost impossible. But there's a place you can go where you can make these kinds of observations, and that is the far side of the moon, where you have thousands of kilometers of rock between you and Earth, where there is no ionosphere, and you can get this pristine look to the beginning of the universe. My guest today is Dr. Christiaan Brinkerink. He's an instrumentation systems engineer at Radboud University, and he's part of the Radboud Radio Lab. They are planning a moon-based mission called the Dark Ages Explorer. This would be a collection of antennae that would be set up on the far side of the moon and would together observe this period of time in the early universe, and could give us some really important answers about how we went from the cosmic microwave background radiation to those first galaxies. How did those first structures start to come together? What was the role of dark matter? What was it like when the first stars were forming? These are the questions that could be answered. In this interview, I talk with Christiaan about the dark ages of the universe. What would it be like to be out in space looking around during this time in the evolution of the universe? What would the Dark Ages Explorer instrument look like? How would it work? And what could we discover about the universe? So enjoy this interview with Dr. Christiaan Brinkerink. Christiaan, the Dark Ages are a region or a time in the universe that is very poorly understood. Can you give us sort of like just a good explanation of what the Dark Ages were?
Yes, of course. So if we look into the night sky with any facility, we look back in time, right? The further you look, the longer that light has had to travel to reach us, and so the further back in history you look. Now, if you keep pushing that, you eventually arrive at what we call the cosmic microwave background. This is the light that started its journey as the universe was becoming transparent to radiation for the first time. It was very homogeneous back then, so matter and energy were quite neatly distributed with only very minor ripples, and from those little ripples eventually structures started to form, which include the galaxy clusters and the galaxies that we currently see around us. That took time. So before the first stars formed from that stage onwards, took several hundreds of millions of years as we currently estimate it. And if you wait a while, so in front of the CMB, closer to us, we can see early galaxies. For instance, the James Webb Space Telescope has been observing those. And so there's a gap between the CMB that is very, very far away and those galaxies that are still far away but closer to us. And that is the time in which structure formation was underway, right? But no stars were formed yet. And so it's very hard to study that period of time in the universe's history, because there's no starlight to observe. So we have to find other ways to study this period. And there's a very specific way in which we can do so, which is by observing the neutral hydrogen that was already floating around at that time. It turns out that hydrogen has a very specific frequency at which it can absorb or emit radiation, which is the 21 centimeter line. And if you observe the 21 centimeter line of hydrogen from that early universe, you can see it, but it will be redshifted to much lower frequencies. So normally it's 21 centimeters or 1420 megahertz. But that would be redshifted to, for us, to, well, a few tens of megahertz. So really by many, many factors, right? As you might recall, the CMB, the cosmic microwave background, sits at a redshift of about 1100. And the galaxies that James Webb Space Telescope observes, they sit at a redshift of, just above 10, 12, maybe pushing 13 at the moment. This changes monthly, of course, as new measurements.
Yeah, it's like 14.4 or something right
now.
now.
So even a bit more than I thought already, exactly. And so you notice that those redshifts have quite a range between them. And that doesn't represent necessarily an incredibly long time, right? We're talking about hundreds of millions of years because the universe expanded quite a bit, relatively speaking, in those early years. But it's a very important stage of the evolution of the universe, and we are blind to it other than studying this neutral hydrogen emission.
So I could have, I want to try and imagine what it would be like to be in the universe at different phases of that early evolution. And the way I've often described it is that early on, say the cosmic microwave background, like when you had that first transparency, it was kind of like the entire universe was the surface of a red star, right? This kind of dull red color, except it was everywhere and everything. And then light could start to, there was gaps opening up where light could, photons could travel, and then they would hit more material, and then the gaps would get bigger and the photons could travel farther. Right. And we're seeing those photons that were able to travel unimpeded throughout the entire age of the cosmos. And so that's kind of hard to imagine. It's the surface of a star, but also it's everywhere. But if you sort of move forward in time, where maybe that cooled down into these kind of larger structures, take us through what it might feel like to be floating in space in the cosmos, say within the first 50 million years.
Oh, that's a nice picture to entertain. So I would imagine that at first it's a dense fog, right? It's hot, it's still quite dense, and the peak of the radiation is, more or less in the optical regime. And as the universe expands and the temperature of this field of radiation and of matter cools down, you will see the surface of last scattering rapidly move away from you as the universe becomes transparent. Of course, it's not transparent to you instantly everywhere. It takes time for that radiation to have traveled enough to inform you of what it has done, right? How far it has traveled. And so I imagine you'd be kind of sitting in a rapidly expanding bubble of transparency, but that doesn't look very regular to begin with. Of course, there are variations in density and temperature in that early universe, and that means that the surface of last scattering has variations in it. It's a bit of a sponge structure, right? It might have areas that get transparent a bit quicker than their surroundings do, or areas that lag behind in this. And so it's this wavy kind of misty surface receding from you, as time goes on. Now, obviously, there are no foreground structures to speak of yet that are observable, right? And so it's a bit hard to estimate the size of this bubble that you would find yourself in as you follow the millions of years after this event takes place, basically. But yeah, that would have to have happened. Something like that, I imagine.
and then though the temperature of this material, this structure that's around you, is going to continue to decrease. It's going to shift out of the visible and into infrared, right? And everything is going to kind of go dark, right?
Yeah, exactly, right. Yeah, and so to the human eye, of course, there would be less and less optical energy to observe, right? The cutoff towards higher energy radiation for a thermal spectrum is quite steep. And so at some point, it will dim to dark red and turn black. And if you have instruments with you, you would still notice plenty of radiation energy flying around, just not observable to the human eye anymore.
And so then we're, is this the beginning of the Dark Ages? Are we now?
Yeah, I would say so. Exactly. Yeah. You would see that most of the hydrogen gets neutral, right? So the charged particles combine to form neutral atoms, basically for the first time since the universe exists, or for the first time since the Big Bang, I should say. That's a bit more accurate.
And then the next event is that the first stars start to form,
right?
But they are inside this, all of this neutral hydrogen that's everywhere.
These dense cocoons of congealed gas, right? That form the first furnaces in which you will see sparks of protostars light up. Presumably first, again, in thermal radiation, concentrated thermal radiation, because of the released energy from gravitational accretion. But eventually, fusion will kick in, and a whole host of new frequencies will start to come out again. Yeah.
But the star is inside this cocoon of this neutral hydrogen. So I guess you're seeing the light is coming off of this new star, and it's light, it's sort of lighting up the clouds that are around it, and the radiation is starting to kick in. It's starting to blow these clouds away.
And of course, that process would presumably take time as well, right? If you have a dense cocoon of partially accreted gas, and somewhere in the core of that structure, stars start to ignite, that light would need time to interact with the gas, maybe start blowing shells of it away, or scatter out of it, or processes like this. So the stars would not be, presumably, immediately visible to the wide environment, right? That would take time to start to break out of those kinds of structures due to the intense interaction of the emitted radiation with
right. And this is one of those big challenges. People always ask, like, why can't we see those first stars? Well, because they're covered in this, they're surrounded by this material. Now, these stars are probably large, probably running hot, short-lived lives, detonating supernova. So, like, what would that be doing?
Yeah, so I think the current picture, but I'm not an expert on this aspect, so I'll have to be a bit careful. But as I currently understand, these initial stars would have an extremely low metallicity, right? Which means they would consist of hydrogen, helium, maybe a tiny bit of lithium, but that's basically it. And if a star has very low metallicity, it means that its layers through which radiation travels as it leaves the stellar core tend to have lower opacities, which means it's relatively easy for radiation to escape. And in a modern star with like a solar metallicity fraction of heavy elements dotted around, those layers are much better at scattering or blocking radiation coming out, which means there's a bigger supporting pressure from the inside of the star to support the structure. That basically means that I think the first stars, these population 3 stars, could be much more massive than modern stars can be. I don't know where the limit is. I'm not sure anyone knows that even for sure. But there has been talk of like 1,000 solar mass type stars, right? So that the things that can no longer exist basically anymore because we no longer have the composition available that those initial stars were made of.
And so those first stars, they're blasting out all that radiation, and they're starting to clear out that area around them. And then I guess the gaps are starting to form where the light can actually make a longer journey, and all of this radiation from the stars is starting to sort of reionize this what was neutral hydrogen around it. And then is this sort of where we're starting to come out the other side of the dark ages?
Exactly. That's what we call the cosmic dawn, that segment. So there's a few things happening at the same time at this phase. You get energetic radiation from those early stars, and that can excite the hydrogen, the neutral hydrogen again. Right? This is the Wouthausen field effect. It's a very particular way in which hydrogen atoms can get excited. Their electrons are bumped up to a higher energy level, and then they decay again to lower energy levels, but that will allow spin flip transitions as well. And the spin flip transition, as you might recall, is what powers the 21 centimeter line. So you reshuffle the energy distribution for this 21 centimeter line, which means you get a brightening of this emission over a certain period of time. But then it starts to abate again because the hydrogen actually gets ionized from the intense stellar radiation that picks up and keeps increasing in flux. And at some point, the neutral fraction of hydrogen will drop so much that you no longer really have an appreciable contribution to the cosmic 21 centimeter signal from the extended hydrogen in the universe.
Right. You only get it from the molecular hydrogen, not from the
atomic hydrogen. So it has some neutral hydrogen. It's specifically an atomic phenomenon.
Right.
Okay. Yeah. Exactly.
Okay. All right. Well, I think that sets the sort of the phase of the universe that we're interested in talking about. And now, you brought this up, but I really want to sort of go a little deeply into why the 21 centimeter line, this spin flip transition, is the right tool for the job. So what is going on that's causing these photons to be released by what should just be this giant cloud of boring neutral hydrogen?
Right, exactly. As you might imagine, if you have hydrogen sitting around doing nothing, there's not a lot going on. There's not any interesting structure that becomes apparent necessarily. And this all depends on how this hydrogen, and specifically the spin temperature of this hydrogen, meaning how many atoms are ready to emit a photon and how many atoms are ready to absorb a photon of the 21 centimeter line. That ratio of energy levels is affected by different processes that happen in the universe. One of them is, for instance, the cosmic microwave background, or what we currently call the cosmic microwave background itself. So the temperature of the ambient radiation field in which the hydrogen sits. If you get hydrogen that is relatively cool, but the effective temperature of this radiation field is high, you will get the hydrogen absorbing this 21 centimeter component of that radiation. Conversely, if you somehow find a way to invert the population to get extra hydrogen atoms excited in terms of the spin flip transition, and then let them decay again, emitting their 21 centimeter line, you will see all that hydrogen in emission. And this is, for instance, what happens when the hydrogen gets excited in a collisional way. So when when atoms of hydrogen bump into one another and can excite these spin flip transitions in each other. So at different stages in the early universe, different mechanisms dominated their interaction with this neutral hydrogen. And this means if you look at a sky integrated spectrum of this neutral hydrogen signal and you look at different redshifts, so you scan at low frequencies in the radio basically, you would see different times at which this signal is seen in absorption, which means relatively cold compared to the background radiation that we get from longer ago. And at some point it starts reaching emission again. So you will get a spectrum that shows a certain wavy structure with different features that illustrate different stages of the strong coupling of the neutral hydrogen gas with these.
That's really interesting to me. So like I had sort of assumed, and obviously things are more complicated than I had assumed, that as long as you have this atomic hydrogen, then you get this spin flip transition. I don't know what the number is. One in some ludicrous number of hydrogen atoms will actually release one of these photons, a very random sort of quantum effect that happens, but it's just the result of you having atomic hydrogen. But it sounds like it's more almost like a geology sort of idea about it's not just the phenomena itself, but it's also the environment that's around it. What are the inputs? What are the outputs that will affect the amount of this radiation that you're getting from these regions, that then tells you a lot more about what's going on than just there's a blob of hydrogen over there.
Absolutely. Yeah, really. Yeah, it's the history of the early universe is imprinted on this signal, right? And so you can read it off and study how strong these couplings were at different times and infer from that what kind of densities there were, right? And how strong the coupling was with the background radiation field. And so this really helps piece together this story of early structure formation in this early universe. You can really, this is a unique way to reconstruct that history. But as you say, indeed, if you have neutral hydrogen sitting around and, you excite it a bit and you wait, this I think the half-life of the decay time scale, right, for neutral hydrogen to emit a 21 centimeter photon is something like, 10 million years or so? Right, for any given atom. So it's a hopelessly slow process that happens. But of course, if you have enough hydrogen, it will happen.
Yeah. And I mean, this process, it's used to find the clouds of hydrogen in the Milky Way. It's used to examine clouds of, intergalactic gas, find reserves of this. But as you say, once you're looking at the very, very early universe, you're seeing this pushed into longer wavelengths because of the expansion of the universe. It's really interesting to me. All right. So then what is the sort of state of the art in us being able to scan for these signals coming from, the 21 centimeter line in the early universe? How do we do that today?
Yes, right. That's a great question, obviously, right? Because this picture has existed for a while. Our knowledge of neutral hydrogen stems from the mid-20th century, the 21 centimeter line, that is. Observations of it have been done in the 50s, I think, already, right? And so there are efforts currently underway to observe this signal from what we call the epoch of reionization, which means when the starlight was destroying the neutral hydrogen and tearing it apart again in its constituent protons and electrons. And there are several different approaches to try to measure this from the Earth's surface already with existing arrays, right? There's several different interferometric arrays that are trying to capture the signal and the patterns it might show on the sky, the scale distribution of variation, basically. And there are several experiments underway that are trying to measure this sky integrated signal, the global signal, we call that. So, of course, in 2018, there was a result published by the EDGES team. EDGES is a dipole antenna instrument in Western Australia. And they have very carefully calibrated their system and tried to understand the behavior of their electronics and of all the hardware that they use as well as they possibly can. And what they reported was seeing this dip, this absorption dip, happening around 78 megahertz or so, and saying, hey, we found something interesting. Please, other people, try to do this measurement yourselves and see if you can report similar features or if it looks completely different for you. And the community still hasn't quite been able to verify this result with other instruments. So the EDGES result still stands there, like, this team found this, but it doesn't quite have the status of this is what the universe was doing at that time, right? So that's a very interesting state to be in, because there's still a lot of uncertainty surrounding what this entire spectral evolution of the global signal looks like, let alone the power spectrum, the spatial distribution of these variations in the signal for any slice of redshift that you want to look at. It's not for lack of trying, it's just very difficult to do.
Is it that it's difficult to do, and you also need the right kind of, because it's more of a custom telescope to make this observation. It can't be an optical telescope. It can't even be necessarily a radio telescope. It has to be this tuned into this exact wavelength in the right. So it's sort of like technique meets the right tool.
Yeah, and it's a weird instrument that you have to build, right? Because the single antenna idea, okay, that's easy to picture, right? You have a single dipole antenna which is sensitive to a range of low frequency radio waves, and you try to calibrate that very carefully and have a good knowledge or control of the surroundings. To measure the spatial variation, you have to build a very weird interferometer, a very strange one, because normally our interferometers that we like to build, they represent a range of spatial scales, right? You have various distances between the antennas so that you're sensitive to very different angular scales on the sky, and you can make great images. That's what we do in EHT, for instance, as well, right? You want to have long baselines, long separations between antennas, but also short baselines, and then a variation of lengths. For an array that observes the power spectrum, the spatial distribution of brightness that comes from the hydrogen, the 21 centimeter redshifted signal, you basically want to pack your antennas very close together. And that has to do with how quickly you reach the desired sensitivity levels. So you want to be able to measure certain scales on the sky a lot, with as many times as you can, because that builds sensitivity, right? The more measurements you have that are sensitive to a particular angular scale, the quicker you reach your critical sensitivity that is necessary to detect the signal in the first place. If you have a very extended array that samples all kinds of different scales, large ones, small ones, and anything in between, it takes a long time to reach your desired sensitivity at any of those scales. And so you're trying to spread yourself too thin if you try that. You would have to keep measuring for a very long time before at any of those angular scales you say, now we have collected enough measurements to be able to say something sensible. So you need to build a very strangely concentrated interferometer where the antennas are almost touching. And basically you want to fill the plane with antennas sitting closely together to optimize your sensitivity and reach it quickly. Of course, the bigger your array, the better, the sooner you should reach your critical sensitivity. But an interferometric array has other drawbacks that you need to contend with, right? You have antennas that occupy different positions in such a dense array. They are close together, so they will start to notice each other. An antenna with other antennas around it will behave differently than an isolated antenna, simply because of the presence of other electrical structures that affect the behavior of this antenna. So its sensitivity pattern, basically. And some antennas will be on the edge of an array, which means that they have a different sight of their neighbors than the ones in the center. And so all these little differences in system response build up and give you uncertainty on what your instrument is exactly measuring. So these are very difficult things that you have to contend with when you want to do these power spectrum measurements. Yeah.
And so your proposal is, we're going to take a very complicated piece of equipment. Let's put it on the moon.
Yeah, it sounds only more difficult, doesn't it?
Yeah.
There is a good reason for us to want to do that, though, because there's a few extra drawbacks that the current experiments have on Earth because of the very fact that they're on Earth. One of the big ones is you can't go as far down in frequency as you would like to properly study the dark ages because the ionosphere is in the way. And at some point, the Earth's ionosphere, or the atmosphere at large, becomes simply non-transparent to this low-frequency radiation that you're interested in. But even above that cutoff, you already notice the presence of the ionosphere. So even if technically you can see the astrophysical sky at, for instance, 50 megahertz or so, you will very much notice the effect of the ionosphere being like a frosted glass kind of layer that you have to look through, which changes all the time as well. And so that can be partially mitigated, and some very nice efforts to this effect have been done by the LOFAR folks. But in order to detect the cosmological neutral hydrogen signal, the far redshifted neutral hydrogen signal, you have to correct for this presence of the ionosphere to a very, very, very high degree of accuracy. And that is, of course, where it gets difficult again. Even if you have in principle a way to mitigate most of it, so you can get very nice looking astrophysical images of other sources nearby, you really have to correct for this. It's difficult to mention a number, but you have to correct everything but a millionth of it or something. Right? Don't pin me on this. I'm not sure about the exact number there. But it's if you have to correct for that far enough, it becomes arbitrarily difficult to do that effectively again. So that's one big reason to actually go to the moon, where there is no ionosphere, at least not the same type that we have on Earth, and so it does not affect these frequencies in that way. That's one big reason. The other reason is on Earth, no matter where you go and sit with your instrument, you very quickly run into issues with human-generated radio frequency interference, right? And that's for partially the same reason as the ionosphere is a problem. If you go to an isolated region, Western Australia, you will still notice leaking radiation from human activities because they can be trapped, right? They can be reflected by the ionosphere and reach your array again, even when they're far over the horizon. That's the same reason that we can reach stations on a continent away on our I think we call them shortwave radios, but that's a bit of a misnomer in this context. And so, yes, human-generated RFI is still a problem, right? Even if you try to avoid it to the best of your ability. Now, RFI typically comes in forms of specific frequencies or narrow bands that have been polluted by this, right? So radio transmitters with bandwidths of several kilohertz, and that show big spikes in your spectrum. And that's a problem because even if they only affect specific frequency ranges in the wider spectrum that you're interested in, all that power has to be handled properly by the electronics in your system. And if there's a lot of extra power that you throw in there, it becomes harder to have your electronics carefully amplify that signal and make sure everything gets amplified linearly. So if there's a lot of power in there, they might saturate in a sense. And that means you can get extra spectral artifacts that are outside of the bands that you're interested in, because you start changing the waveform that you amplify. And that's a very bad effect, of course, as well. So it helps, if no RFI is present, to simply limit the necessary dynamic range that your amplifiers need to have. That makes things more tractable in an electronic sense of the word. So that's the second big reason. Yeah.
Right. So you're no longer having to worry about the ionosphere, and you could resolve that with a space antenna. But
exactly right. So that would provide a reason to go outside of the atmosphere. Now, avoiding RFI, again, a thick ionosphere layer that blocks most of the human-generated emission will still let some leak through. So even if you're outside of the atmosphere but close to the Earth, you will still hear this RFI stuff, and it will still be a problem. So that means you would like to have yourself shielded from that by some body, right? And the moon is, of course, a perfect object that could do that for you. Now, of course, that comes with the added benefit that deploying something on the surface of the moon gives you a stable geometry of your array that you can learn to calibrate very, very well, and not have changing geometries or relative positioning of your antennas that changes all the time. So that's, you want a platform for a stable interferometer, you want shielding of RFI, you want to avoid the ionosphere. And the perfect spot that checks all these boxes is the far side of the moon.
Oh, it's interesting. I didn't think about the changing landscape. I guess on Earth, you're going to have people making buildings, trees are going to grow, that the actual landscape around your antenna is changing, and that's going to have an influence. But on the moon, nothing is changing.
Absolutely, yeah. So the SARAS-3 experiment, for instance, in India, has an antenna that is floating on a lake, right? So that means that the direct environment should be, quite stable because there's not a lot of different geometry happening around it. But I think one of the results demonstrated that they're actually already sensitive to the geometry of a tree at the shore of the lake. Whether it being there or not somehow affects the antenna pattern. So you're really sensitive to those kinds of variations in your direct environment. Yeah.
So then what would the Dark Ages Explorer telescope look like on the moon? Again, if you're an astronaut, you fly to the moon, your job is to maintain the observatory. What does it look like?
So we envision a dense field of antennas that are very close together, but deployed in a very controlled way so that their relative geometry is well known. So they might be sitting close together, but their orientation would be consistent. Their height above the surface would be very consistent. And so the array has predictable properties in that sense, at least.
So how close?
A fraction of their own length. So we're talking about separations of like 10 centimeters or so.
Oh,
between
wow.
antennas
Okay.
that are each 1.5 meters in size or so. Yeah.
Right. So these antennae are like 1.5 meters tall, but they're within 10 centimeters of each other. So they're packed in.
Yeah, really packed.
tight.
Yes, that's actually quite important. So you densely sample the aperture, as we call it. The other thing is that these antennas are likely to be two-dimensional, as in flat antennas. Meaning dipoles. So the edges antenna, for instance, it looks a bit like a table that's split down the middle, right? You have two of these blades that form the two poles of the antenna. So together they're a dipole, and you measure a voltage difference between these blades, right? And that gives you your signal. So we are talking about flat antennas, but actually flat as in deployed close to the lunar surface, but without appreciable 3D structure to them. And they basically need to be this way because otherwise the mass of each of these elements very quickly becomes too high to be deployable by any single system. Because the size of such an array already needs to be appreciable in order to start pushing into this redshift range that we're interested in. And when I say that, I mean, if you have an array of about 1,000 antennas, so with the size I mentioned earlier, 1.5 meter antenna sizes, you get a size that is like something like 50 by 50 meters, right? So, not titanically big, but still sizable and beyond anything that has been deployed on the lunar surface so far. So that is an array that would allow us to push into redshift space up to a redshift of 27, 28, something like that, which is, somewhat beyond what current efforts on Earth could realistically do, I think. But of course, if you want to push further into the redshift range, so further back towards the CMB and into the proper dark ages, you will need to build larger arrays still. The size of the array that you need to reach redshift 50 or so, which is, solidly in the middle of the dark ages, that becomes easily on the size of a square kilometer or so.
Right. So you're saying let's build the square kilometer array, but let's build it on the moon.
Indeed, yeah.
Yeah.
As I love to say about this, nothing about this is easy.
Yes.
Everything is hard, right? Building a square kilometer array on Earth is a very, very big project. And so we have to think, how simple can we make such a system and still have it be able to do the science that we would like to do. And yeah, we have certain advantages on the moon, right? So a stable environment, there's no changing weather circumstances. Thermally, the swings are big, but you are stable for a while, right? So the days and the nights tend to be 2 weeks long, right, on the moon. And so that might help us a lot as well. So we don't have to deal with the degree of variations that an Earth-based environment gives you. But other than that, the hardware needs to be simple, it needs to be hardy, and it needs to be very low mass. And that is, of course, where we see most of the work in front of us, right? This is not an array that we can build with current day technology, right? So we did a study together with ESA in 2021, I think it was, 4 years ago, where we said, okay, we want to build an array like this, right, on the lunar surface. How far could we get with currently mature technologies? And the outcome of that was, well, if we really try right now with what we have and the technologies we have experience with, we might be able to build a 4x4 antenna array with a little rover that deploys everything and all the ancillary systems that you need, electrical harnessing, power generation, stuff like that. And a 4x4 array, it sounds really interesting, but it doesn't connect yet to the science that we want to do. We really need a larger array for that. And so there are several avenues in which we need to develop technology in order to make something like this close to possible, right? And there's at least like 5 different ways in which technology needs to mature to make this possible. So antenna technology based on foils, for instance, that greatly reduces the mass per antenna element. A predictable and reliable deployment system that has a minimum of mass overhead, but that allows us to have a great degree of control over where we place these antennas specifically on the lunar surface. For instance, electronics that need to be located close to the antenna terminals, where the initial amplification takes place of the signal, these need to be able to survive a very large range of temperatures, right? And that is, of course, easily a problem for electronics, right? You get differential expansion and contraction, you get contacts that get damaged, and a few other effects. And so you need to think very carefully about your thermal management there. And there are some very interesting ideas floating around in the network that we work with to develop this to a much higher degree of maturity.
ESA has been doing a lot of research into in situ resource utilization, that mining various elements and stuff out of the surface of the moon and then using that, 3D printing it and so on. Do you see any part of this? I mean, it already sounds like it would be hard to build on Earth. Do you see any pathways where maybe you can develop parts of the structure out of the lunar regolith and then deliver the electronics or the more fine-tuned components?
That's certainly an approach that is being thought about. Specifically by our colleagues in the US, which is the far view concept, right? That was published a while back. And this is like 100,000 antenna element array that would mostly use locally produced elements, specifically the antenna material itself, extracted from lunar minerals. This is not a way in which we have thought about it yet. We want to realize a system that can be delivered with a single lander. So avoid the need for multiple landers. That greatly complicates the logistics, but also the engineering challenges of the mission. So we envision a single lander with a payload capacity of, well, at this point we are entertaining the idea of 1.5 metric tons, so 1,500 kilograms, because that is the envisioned payload capacity of the Argonaut lander, more or less. So we are trying to make it connect to capabilities that we envision having in maybe 7 years or so, right? Maybe a bit sooner. I'm not sure how the timeline will work out. And that means that the concept for the array that we are thinking of is still somewhat modest in size. It's this 32 by 32 antenna array, because we think we have a shot at making this possible with sufficient technology development, even though we know that such an array size is not yet able to address the deeper redshifts, right? The higher redshifts, further back in time and deeper into the dark ages. So to realize that, you either need a lunar economy, where you have production facilities on the moon that are able to produce most of the materials you need for a system like this, maybe with the addition of a few lower mass components that would be extremely hard to produce on the moon, like detailed electronics. But that is a step beyond this concept. This concept really focuses on what we might be able to deliver there with a single lander. We are not explicitly yet thinking about in situ resource utilization. That is a natural step to think about, but we're just not there yet.
Yeah, no, I mean, the Argonaut, this is the Europe-based landing system that's being proposed right now. Yes. But I mean, that's just one possibility. There's, of course, the work that's being done by Blue Origin and SpaceX, of course, with Starship. And that you might be looking at tens of tons of material delivered to the lunar surface. So, you must have done some back of the envelope calculations thinking about the potential, lunar payload of those kinds of services.
Absolutely. And the nice thing is the stringent limitations on payload mass for the Argonaut program mean that we really have to scrape away all the extraneous mass of a concept like this. But once you have it, a bigger payload capacity allows us to easily scale up the concept. There's nothing standing in the way of deploying 4 copies of such an array with, of course, the necessary adjustments to the data infrastructure, for instance, and making this a much larger array if you can fit multiple instances of such a payload in a larger lander, right? Because we've already optimized it to be as low mass as possible. So give us a total mass budget and we can say how many antennas we will be able to bring and adjust the concept accordingly. Yeah.
So let's talk about some of these scientific questions that you're hoping to answer. So let's say you things have gone well, you've got a delivery on an Argonaut, your array has been set up properly and it's operational. What kinds of signals from which parts of the universe and times and what answers, I guess, what story does this start to tell you about the early history of the universe?
Right. So the earliest redshift at which the cosmologists expect to find interesting signals is a redshift of about 200, which is, sits just above 7 megahertz in frequency, basically. That's where you might start to see the first interesting change in coupling of this neutral hydrogen to what is happening around it. That's where this ratio of coupling strength starts to change for the first time. And so the dark ages take us through that period from a redshift of about 200 to a redshift of about 30. And there we expect to see this big dip, this absorption dip, this relatively cool hydrogen that is backlit by the presence of the radiation field flying around at that time already. And that should show us the first stages of structure formation. Now, that stage of the frequency range and pertaining to the dark ages is thought to tell us a lot about the fundamental physics that are going on at that time. Meaning, the process that happens is very simple. You get minor density and pressure variations, and that start to be amplified because the overdensities start to contract, the underdensities start to dilute, right? And the pace at which this happens already tells you a lot about the role of dark matter in this, and about how soon these structures can start to form that yield stars that emit light again. So the physics of that region the physics of that frequency range are very simple. At least that is currently thought to be the case. And so you can very directly connect it to fundamental physics and maybe particle types that we are not quite aware of yet. If you move beyond that and go into the cosmic dawn phase, where you start to see starlight starting to play a role, that brings you into basically a second epoch of absorption. And there the story starts to become much more complicated, because on top of the fundamental physics that initially happens, you now have the astrophysics of starlight and emerging structures and ever more heterogeneous areas in the universe that behave very differently from one another existing at the same time. And so there you can tell more about the astrophysics, about the pace at which stars get formed, maybe the masses of those stars, certainly the masses of the halos that are forming, and the sizes of the structures that are coming out. But that involves certainly many more parameters that you need to worry about, right? So that is basically between redshifts of roughly 30 and 16, I believe. That's the breadth of this absorption, the second absorption dip of the cosmic dawn. And so redshift 16 and lower, so what's that? That's about 80 megahertz and up or so, maybe a bit higher, maybe 90 megahertz or so, and up. That is basically the epoch of reionization, where you see the starlight really destroy most of the neutral hydrogen in the system and unbind it again, basically. And that is, of course, a region that current research is also already focusing on from Earth. Yeah.
So if I could take the answer to a question that you have, put it in an envelope, and hand you the answer, and you're thinking what, you've got some question, are we alone in the universe? And then you open up the envelope,
and they might say,
as it relates to your research, what would be like a really exciting result that you would love to to see come out of this entire, it's 20 years later, we've got the lunar telescope, finally they've done the first run, they've got their answer, you're looking at it, what is the question, and what is the, the kind of answer that you're hoping to, what is the question, I guess?
Yeah. Right. I think a big question is, what's the deal with this dark matter stuff? What's going on here, right? Are we fundamentally misunderstanding how to model an aspect of gravitational interaction, or is it actually honestly a different type of matter, particle, substance, field that we interact with in some way, but that we can't detect in any other way? Is that actually the right way to look at it, or is there a very different way in which we need to think about this phenomenon? That's a big question that I hope we learn about when we understand this initial structure formation better.
We see the ratios of it in the cosmic microwave background radiation, and of course we see it through other observations like gravitational lensing and things like that. But you're saying that you would see another signal of its influence in the dark ages.
Yeah, basically because as you concentrate matter ever further, the only way that dark matter can cool is through the emission of radiation by baryonic matter, right? And so the interplay between these two species, according to this model, at least this is still talking about the context of the standard lambda CDM model. There's a very intricate interplay between how quickly these structures can form. And it seems that we are missing some fundamental insight here, because we are getting strange results of galaxies that are formed already quite early in the universe, right? JWST seems to see clear, bright, massive galaxies at a time where no one really expected them to exist quite yet. And so it seems that the vanilla model with using lambda CDM, it doesn't quite seem to fit perfectly nicely with what we're measuring nowadays. And so if we compare further back in the history of the universe, we might be able to finally connect the dots there and see what the natural evolution from the CMB and its ripples is to those fully fledged large structures that have formed somehow sooner than we thought they could.
And is this partly that dark matter now is a lot more diffuse and doesn't seem to interact with itself or with regular matter, but early on in the universe things are a lot more dense, and that dark matter would be forced to interact with itself and with regular matter in ways that could be detectable, maybe through that 21 centimeter line?
I think, it's still an indirect measurement, so I think we would still be talking about gravitational interaction. But the pace of that really needs to be kept up in order to fit to the modern universe, basically, right? And so we need to somehow compress that time scale of structure formation into a shorter amount of time. How did that happen, right? How did this work? What was the excuse for matter to behave this way? What accelerated this process? And I think that's a very interesting, close to fundamental physics question that we can start to address if we properly study this epoch.
Yeah, I guess where I was going with this is that there's a lot of really interesting research into what happens if you put dark matter into fairly constrained spaces? What if you put it inside a star? What if you put it inside a planet? Will it self-annihilate? Will it create additional heat that is detectable? And so, you talked about this, that there's different factors that are influencing the production of the 21 centimeter line photons. And so if you did have this dark matter compressed early on in the universe, and still lots of it, is there some kind of additional influence that it's contributing to the flux of the 21 centimeter line?
I would have to speculate a little bit, right? Because I'm mostly on the instrument side, and so this is talking about details of cosmology that I don't know a lot about. But I do think that in the early universe, of course, the average densities were higher. But I'd also think that the cuspiness of dark matter distributions would be dominated by very small scale structures. So dense cores of galaxies, or maybe even individual stars. And so those are very small scale concentrations of matter that might harbor higher concentrations of dark matter. Although, if you look at galactic halos and stuff like that, it seems to be very dilute, right? I don't think we have any evidence of a higher cuspiness of dark matter distributions at the present day, at least. We don't see any phenomena that need that as an explanation.
That's really cool. Christiaan, what are you obsessed with?
Well, fundamentally, I love figuring things out, right? And this has two specific aspects. One of which is what's going on in the universe. How does anything exist at all, and why does matter behave the way it does? Right? That's a bit big, but I try to make small contributions to that. But the other thing is, how do we convince nature to give us that information? Right? And it's very nice because in astronomy, you don't have the luxury of setting up your experiment. You can't smash stars into each other or strew some hydrogen around. You have to very carefully look at what is going on. And for that, you need to develop very, very clever tricks to optimize the sensitivity of your instrumentation, the measurement principles, how to cancel sources of error, things like that. And I absolutely love thinking about clever ways, ever more clever ways, to improve our ability to measure things of the universe. I think that is a very, very exciting endeavor. And I'm sorry if it sounds a little bit too abstract, but that is actually honestly the side of the work that I would say I enjoy the most, which is why, of course, I'm working at an instrumentation center, right? This is exactly the right place for me to be. Yeah.
No, I totally get it. There's got to be moments where you're looking through some technical paper and maybe even a different field, and people have solved a problem in communicating underwater with sonar, and they did it with something, or I think about, say, LIGO, where they used quantum squeezing to be able to improve on one axis. And I'm sure you walk away and go, how could I sort of exploit quantum mechanical effects to discard parts of the uncertainty that I don't care about so that I can grab more of the part that I do care about?
Exactly. Yeah. That's a great example of how incredibly clever the LIGO Virgo team has gotten with the squeezing of the laser light, right? And it's just amazing that kind of measurements have gotten possible, right? And this is specifically about the nature of the detector they use and the laser light, and that they manipulate it in a very clever way to gain another order of magnitude and sensitivity. And in radio receivers, there are all kinds of other tricks that you can use to cleverly tease out the relevant information about all these wave fronts that are impinging upon us. And that is to me a very exciting notion. And in a somewhat of an abstract way, right? I can't immediately point at a key trick that I say, I like that one the best. There's a whole book of recipes that has been involved, and all these receiver systems have built on so many clever little tricks and technologies that they really are quite impressive feats of modern engineering, I would say. Yeah.
But there's like a part of your brain as you're reading the news, watching anything that's going, is there something here that I can try, that I can use, that I can exploit?
Right. Yeah. So there's been talk of a fundamentally different type of antenna, for instance, right, where you use what's it called, a hovering cloud of atoms instead of a linear conductor, and that cloud of atoms might be extremely sensitive to particular excited vibrations induced by passing radio waves. And that's a very early stage idea that people said, hey, look at this thing. It apparently is very sensitive to that effect. And then, of course, as scientists and engineers, you immediately go, wait, is there a way we can exploit this? Is there a way we can get our antennas to be 1,000,000 times more sensitive? How can we tease this out of that, right? How can we convince nature to help us a little more there? Yeah.
All we have to do is change what a radio telescope looks like at a fundamental level. That is not a wire or a dish that's pointing in the sky. It's some chamber that's levitating hydrogen in it, right? Like
exactly. Which we actually, in fact, already have. We use the masers for clock stability in the VLBI experiments. Yeah, but no, I appreciate your point. Indeed, it might lead to systems that are completely unrecognizable from the ones we currently use. Yeah.
No, I absolutely get that fascination, and I think for me, that's what I find so interesting is the more of these fields that I report on, the more I see these connections, and the more you can kind of see this process working. I try to connect people together when I think maybe there's a connection that they haven't noticed yet, but still it's a great way to kind of just approach it, that you're constantly, you've got this sort of net that you're constantly casting as you're moving through the literature with this sort of open mind and creativity and that allows you to then solve problems in what you're working on. Well, Christiaan, it was absolutely fascinating to talk with you.
Yeah, pleasure.
And good luck with getting the Dark Ages Explorer operational and giving us that insight into a time that is, perhaps one of the last frontiers in what we can observe in the universe. And hopefully it too will fall eventually.
Thank you so much, Fraser. It was a pleasure talking to you.
Thanks a lot. I hope you enjoyed this interview with Christiaan Brinkerink. Now, I've got a longer version of this interview. We changed topics and discussed the Event Horizon Telescope. Christiaan is part of the team that is looking into setting up a new telescope to join the network in Namibia. And it's actually very complicated to find the perfect spot, a place where you've got a minimum amount of influence from water vapor in the air, and how can you choose the right spot? What is the right instrumentation? So if you're interested in the Event Horizon Telescope, you'll probably enjoy that additional interview. It's over on Patreon. It's completely free. You can just access it right now. You don't have to sign up. You can just watch the same version of this interview, but with additional content. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Barry Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nelson, David Giltonan, David Matz, Dusty Cable, Evan Pro, Greg Feely, Hudson Ward, James Clark, Jeremy Mattern, Jim Berg, Jordan Young, Marcel Smith, Michael Purcell, Modsel, Paul Roebuck, Rank Kaidu, Robeck, Sean Sargent, Stephen Fowler-Melly, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level. And all our patrons, all your support means the universe to us. I really enjoyed this interview, and I really enjoyed the conversation that we had at the end of the episode about how you can sort of get these great ideas and inspiration from lots of different fields. And I was talking with Christiaan after we completed the interview, and he has a degree in aerospace engineering, and then a degree in radio astronomy, and then a degree in the actual radio instrumentation that he does. And so you can sort of think about he's perfectly adapted to be thinking about what it might take to be able to put a radio telescope on the far side of the moon. There's part of it about aerospace engineering, about the actual kind of instruments that would have to be put together and to be able to get them there, the kind of observations that you're going to look to make with radio astronomy, and then the actual building the components that would make this all come together. And you can just see how valuable it is to look outside of your field, not just at what you're working on specifically, but other fields, and get inspirations. There's a lot of overlap. And, he just hit the nail on the head for me for that. And I found that so great. So I hope you enjoyed this interview with Christiaan Brinkerink, and I hope you're looking forward to the Dark Ages Explorer instrument. Hopefully it will fly to the moon. All right. We'll see you next time.